Okay. Hi, I'm Madeline McCullough. Today, let's begin talking about Newton's law of universal gravitation. This law tells us that every object in the universe attracts every other object. The strength of that attraction depends on two things: how massive the objects are and how far apart they are. Specifically, the gravitational force is proportional to the product of the two masses and inversely proportional to the square of the distance between them. This law explains not only why things fall to the ground, but also why planets orbit the sun and moons orbit planets. It's a fundamental principle that governs all motion due to gravity, from everyday objects to massive celestial bodies. This concept isn't just theoretical, it's extremely important in several scientific fields. In astrophysics, for example, understanding how gravity works helps us study how galaxies form by looking at the gravitational pull between stars. In astronomy, we use gravity to predict the orbits of comets, moons, and other celestial bodies, including calculating when Halley's Comet will return. In aerospace engineering, engineers rely on gravitational calculations to plan satellite paths or spacecraft missions, like figuring out how to reach the moon. Without Newton's law, we wouldn't have accurate GPS, satellite communications, or even space travel. The foundation of this law was built over centuries. In the 1500s, Galileo Galilei studied falling objects that showed gravity acts equally on all masses. His work laid the groundwork for Newton's theories. Then in the 1600s, Johannes Kepler described how planets move in elliptical orbits, which Newton later used to support his law of gravitation. Finally, in late 1600s, Isaac Newton formally introduced the law of universal gravitation, stating that all masses attract each other. Later in 1798, Henry Cavendish conducted a famous experiment using a torsion balance to actually measure the gravitational constant, which allowed scientists to calculate the Earth's mass. Each of these scientists played a critical role in developing our understanding of gravity as we know it today.
My name is Michael, and I will be going over major objectives 2 and 3. 2.1 Original experimental process. Sir Isaac Newton did not conduct an experiment in finding the universal gravitation law. Instead, he utilized a combination of observation and mathematical reasonings to develop his theory. Isaac Newton laid the foundation for classical mechanics and changes the way we understand the forces that govern motion in the universe. It was not until Henry Cavendish, who conducted an experiment in the 18th century, that was pivotal in measuring the gravitational constant. That experiment used a torsion balance, two small spheres, and an enclosure. The procedure of the experiment consisted of alignment and measurement of the spheres where the spheres were positioned symmetrically, and the gravitational attraction would cause the rod to twist. By measuring the angle of the twist, knowing the torsion's coefficient of the wire and weight of the spheres, Henry Cavendish laid the groundwork for calculating gravitational attraction in the laboratory setting. Slide 2.2 Difficulties. Cavendish's equipment was remarkably sensitive for its time. Air currents and temperature were difficulties Cavendish had to face during his experiment. To overcome these challenges, Cavendish placed his entire apparatus in a mahogany box about 1.98 meters wide, 1.27 meters tall, and 14 centimeters thick, all in a all in a closed shed on his estate. Cavendish's ability to produce accurate results were one of the challenges he had to face during his experiment. However, in 1895, C.V. Boyd's experiment exceeded Cavendish's experiment results. 2.3 Motivation. Isaac Newton was inspired to make the connection between falling bodies and astronomical motions when he saw an apple fall from the tree and realized that if the gravitational force could extend above the ground of the tree, it might also reach the sun. He sought to understand why the moon orbits the Earth and why objects on Earth fall to the ground, leading him to propose a single force of gravity that governs both celestial and terrestrial phenomena. 2.4 Original benefits. Since Isaac Newton did not perform an experiment in finding universal gravitation, I will talk about the benefits from Henry Cavendish's experiment. Henry Cavendish's experiment was important because it helped us figure out the gravitational constant, G, which is key in us understanding how gravity works, and his experiment helped us learn a lot more about gravity and how it affects the Earth. Slide 3.1, modern experimental process described, the torsion balance method. Similar to Cavendish's original method, modern experiments often use a torsion balance, but with more advanced materials and equipment. A light beam is used to measure the angular displacement between the two masses. Laser interferometry can enhance accuracy by measuring the minute twist in the balance with extreme precision. 3.2 Differences in modern approach outline. As stated in previous slide 3.1, with the torsion balance being the main equipment in measuring gravitational constant, the advancement with the laser interferometry and its ability to enhance accuracy in measuring the twist and balance with extreme precision. Slide 3.3 Modern benefits of discovery explained. Fast forward to today, the modern understanding of universal gravitation has led to numerous benefits across various fields of science and technology. Space exploration. Newton's formula helped engineers work out how much energy we needed to break the gravitational bonds of Earth. The path of every astronaut and the orbit of every satellite from which we benefit, whether from communication, Earth observation, scientific research around Earth or other planets, global positioning information. With the ability to now put satellites in space, that changed the way we communicate forever. It improved our gravitational understanding and allowed engineers to place satellites in the right spots. And slide 3.4 Future expectations of research discussed. In the coming decades, scientists and engineers are likely to pursue various innovative initiatives leveraging the principles of universal gravitation. Space exploration, with us understanding the gravitational interactions, engineers may design innovative spacecrafts that efficiently navigate gravitational fields. And gravitational wave astronomy, this technique will allow us to better understand the most massive objects in the universe, such as black holes, neutron stars, and supernovae, and it will provide us with a new window to study how the universe formed.
Hi, my name is Christian Fields. I'll be going over major objectives 4 and 5. A person wants to build a pulley on the side of a cliff to transport items up and down. Before buying supplies, the person needs to figure out the height of the cliff. To avoid air resistance, the person drops a metal sphere down the side of the cliff and finds that after 3 seconds, the sphere hits the ground. What is the height of the cliff? 4.1 Law of universal gravitation and acceleration of gravity on Earth. Newton's law of universal gravitation states that every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. When applying law to Earth's surface, we find a constant value for the gravitational force due to the mass of the Earth being so large. Taking the formula for universal gravitation, we find that gravity equals approximately 9.8 meters a second squared. 4.2 Benefits of understanding acceleration of gravity. We can apply Newton's law to objects on Earth to better visualize and understand the law on Earth. Having a value for gravity on Earth gives us a tool to make the law into a measurable concept. We can test gravity on Earth to progress and make sense of more complex concepts. Ultimately, gravitational acceleration helps us in topics of engineering, technology, space science, and more. 4.3 Process of writing example questions. The example question is not too simple. It uses kinematic equations, and the student needs to know how to interpret and apply the values. The question isn't too complex. Understanding the basics of an object at free fall is enough to solve the problem. 4.4, comparisons and contrast. The example is like other problems in the textbook because it is a basic concept of gravity on Earth. It differs from the textbook because it's combined into a real-life scenario. It was meant to make the concept more applicable to the student. 5.1 is going to be the table using kinematic equations for the data. Wait, hold on. Using kinematic equations, the data table was created. Position, velocity, and acceleration was found at 1 second intervals. 5.1 graphs. Acceleration versus time, we have a constant value of 9.8 meters a second squared. Velocity versus time, we have a constant decline starting at 0 since the object started at a resting position. Position versus time, we have a curved decline starting at 0 since the initial position was considered the starting point. 5.2, formulas and constants. These are the kinematic equations for objects in free fall where acceleration equals negative gravity. Constants are going to be initial velocity in meters a second, initial position in meters, time in seconds, velocity in meters a second, position in meters, acceleration of gravity at 9.8 meters a second squared. 5.3, solving the problem. The starting position will be 0 meters and the position will be negative y since the sphere is falling. The initial velocity will be 0 meters a second since the sphere will start from rest. Plugging in our values, we find that at 3 seconds, the object falls 44.10 meters. 5.4, verifying the solution. Using the other two kinematic equations, we can work backwards to verify our work. Since the calculations lead to gravity equals 9.8 meters per second squared, we have verified our calculations for the example question are correct.
Hi, my name is Christina, and I'll be going over the summary conclusion, which is 6.1 through 6.4. Beyond the apple, Newton's legacy in science. Despite formulating his law of universal gravitation in the 1660s, Isaac Newton waited over 20 years to publish these groundbreaking ideas. The Principia Mathematica 1687 finally revealed his work following decades of refinement and development. Newton's genius extended far beyond gravity. His simultaneously revolutionized mathematics by developing calculus, conducting pioneering experiments with prisms that established a theory of color, and formulated fundamental laws of motion that still govern physics today. Though somewhat reclusive, Newton engaged in notable scientific relationships. Edmund Halley of Comet fame believed so strongly in Newton's work that he personally financed the publication of Principia. Meanwhile, Newton maintained famous rivalries with Robert Hooke and Gottfried Leibniz over intellectual property disputes, demonstrating how scientific advancements often emerges through both collaboration and competition. 6.2 Beyond Newton Reflections and Surprising Discoveries. While doing this project, we became interested in Isaac Newton's schooling and education. Turns out he attended Trinity College in Cambridge in 1661. He was older than most of his classmates as well. Our explorations revealed surprising aspects of Newton's life and work. Contrary to expectations, Newton was initially an exceptional student and developed his groundbreaking ideas through pandemic isolation, and Cambridge closed due to plague. His revolutionary work on gravity emerged not from the collaboration of laboratory environments, but through a solitary contemplation, a stark contrast to modern scientific practice. Newton's gravitational research spanned decades, evolving gradually rather than through sudden breakthrough. While resources consistently acknowledge gravity's importance for space travel, the direct application remains somewhat opaque in history accounts. Modern extensions of Newton's work included research on black holes and gravitational waves, continue expanding his legacy. While Einstein's gravitational time dilation affecting GPS satellites demonstrates how classical mechanics connects to contemporary technology. 6.3 Summary of topic and project process. This project focused on Newton's law of universal gravitation, a groundbreaking discovery that showed how all objects in the universe attract each other based on mass and distance. We explore not just the science behind it, but also the historical background, Newton's personal journey, and the law's impact on both everyday physics and space exploration. The development process went smoothly overall. Each group member contributed research, slides, and ideas, and we collaborated to everything organized and on schedule to keep everything organized and on schedule. One of the most important parts of the topic was realizing how one idea could connect motion on the Earth to motion of planets, making it one of the biggest scientific breakthroughs of all time. As for the project itself, the most important takeaway was learning how to break down complex science into something understandable and engaging, especially through visuals, examples, and real life connections. It helped us practice working on it as a team while building a stronger appreciation for both science and its history. 6.4 Relevant source. These are the sources for the project from 1.2 through 1.4. Continuing, we have relevant sources for 2.1 through 3.4, and then continuing, we have 4.1 through 5.4.